This is lesson 9.4 and 9.5, negative exponents in scientific notation. Okay, so to start with negative exponents, we'll first observe a pattern that happens with exponents using what we already know of exponents, because really when you look at something like 3 to the negative 1 and 3 to the negative 2, that doesn't really have an obvious meaning in terms of what an exponent is. How could you use 3 as a factor negative 1 times, or 3 as a factor negative 2 times? So let's look at a pattern here. We know 3 to the third is 3 times 3 times 3, which is 27. We know 3 squared is 3 times 3, which is 9. 3 to the first is 3. 3 to the 0, anything to the 0 power we know is 1. And here's where we're not quite sure, because, again, negative exponents don't really make a whole lot of obvious sense. So let's look at the pattern in these numbers. Well, to get from 27 to 9, we would divide by 3. To get from 9 to 3, we would again divide by 3. To get from 3 to 1, we would, divide by 3. Because you're losing a factor of 3 as you go down in each of these exponents, you're dividing by 3 each time. So then if we went one step further and divided by 3 again, 1 divided by 3 is just 1/3. And if we go one more step further and divide that by 3, 1/3 divided by 3 would be 1/9. And if you think about this, remember 9 is just 3 squared. So we see how we have 3 to the first is 3, and 3 to the negative 1 is 1 over 3. 3 to the second is 9, 3 to the negative second is 1 over 9. So we see the relationship between the positive exponents and the negative exponents on each of those. Right, to give you further explanation or rationale for why this works, let's first look at something like this, where you have division, but the denominator has the bigger exponent. Let's look at this first using the exponent rules. So what we learned in section 9.3 was that when you have division with the same base, you subtract the exponents. So this would be x to the 3 minus 5, or x to the negative 2. 3 minus 5 is negative 2. If we do the same, if we simplify the same expression using the definition of exponents, we know what x to the third is. That's x times x times x. And we know what x to the fifth is. X times x times x times x times x. And we can cancel any common factors of x in the numerator and denominator. So there's 1, there's 2, there's 3, and all we're left with on the bottom is x squared. And since these have all canceled out, think of there as being a 1x times each of these, so all we have left is a factor of 1. So we see how these two are the same thing, x to the negative 2, 1 over x squared. So that brings us to our rule that defines negative exponents. For a not equal to 0, and any whole number n, a to the negative n is the same as 1 over a to the n. So for example, 6 to the negative 4 is the same as 1 over 6 to the 4th. Okay, so let's do some examples of these. First thing we want to do is write each expression using a positive exponent. So this is 3 to the negative 5th. If I want to change this to a positive exponent, I need to write it as a fraction with this expression in the denominator. So this would be 1 over 3 to the 5th. Same thing with y to the negative third. If I want this to be a positive exponent, I write it as a fraction with this in the denominator, as y to the positive third. We can do the same thing in reverse, write each fraction as an expression using a negative exponent. Well, here the 6 to the third is in the denominator, so if I write this so that it's not as a fraction, it would be 6 to the negative 3. Now here, there's no exponents involved, but we can first write 25 as 5 squared. And now we can actually change this to something using a negative exponent. Since it's in the denominator, if I were to rewrite it, that would be 5 to the negative 2. And we'll do the same thing with c. We need to first rewrite 27 as 3 to the third. And now to write that as a negative exponent, it's in the denominator, so this would be 3 to the negative third. Okay, Now, sometimes in math, it's more helpful to have positive exponents, whether they're in the numerator or denominator. Sometimes it's better to have positive exponents. Sometimes we just want to avoid fractions completely, and we'll use negative exponents. So there's no really correct way, so to say that your answer should always be in them. There's no way to say that your answer should always have positive exponents, or that they should always be just a single expression with no fraction, even if it's a negative exponent. Sometimes one is more useful than the other, and you'll actually see that when we talk about scientific notation in a few minutes, that sometimes writing it with a negative exponent is perfectly fine. So just be able to convert between those two. Alright, so there are 2 try it yourself problems for you to work through. So pause the video and answer those 4 questions, and when you're ready to check your answers, press play to continue. Alright, the first one is 1 over 5 to the 4th. This one is 1 over m squared. This is 6 to the negative 2. And this is 8 to the negative 4. Okay, let's try another example on the next page. Evaluate each expression if m equals 4 and n equals negative 3. Alright, so we've done stuff kind of like this before, but now we're going to have some things with negative exponents involved. So, same thing though, we'll go ahead and substitute the values that we have. So, m is 4, so this is 4 to the negative 2. Well, we know from our definition of negative exponents that I can first rewrite this as 1 over 4 squared. This right here does not make a whole lot of sense. I can't just start figuring out what this number is because this negative exponent doesn't make sense. It doesn't tell me how many times to multiply by 4. So we first write it with a positive exponent because now I know what 4 squared is. And 4 squared is 16. And we can leave our answer just like that, 116. Alright, let's look at B. This is 6m n to the negative 4. So let's see, we have 6, m is 4, and n is negative 3. And notice here that the n is the only one that's raised to the negative 4 power, not the m and not the 6. It's 6 times m times n to the negative 4. That's one whole thing all by itself, and it's the only one that has that negative exponent. So now when we're multiplying these, this is the only one that needs to be rewritten. So this is just 6 times 4, and then times, we'll change this to a fraction, so it's 1 over negative 3 to positive 4. Notice that the sign of the exponent changed, but the sign of the number stayed the same. I'm not changing this negative 3, I'm only changing the sign of the exponent. Okay, and we know how to multiply numbers. 6 times 4 is 24. And then negative 3 to the 4th. That's negative 3 times negative 3, which is 9, times negative 3, which is negative 27, times negative 3 is positive 81. And we know how to multiply fractions. We can write this as 24 over 1, and then we can cancel a common factor here of 3. Oops. 3 goes into 24 8 times. There we go. And 3 goes into 81 27 times. So this is 8 over 27. Okay. So go ahead and pause the video and work through the try it yourself problem here. And when you're ready to check your answers, press play. Alright, for this one you should have gotten negative 1/4. Okay, negative exponents are often used in science when dealing with very small numbers. In example 4 says an atom is a small unit of matter. The smallest atom has a diameter of approximately 1/10 of a nanometer, or 0.00000000001 meter. Write the decimal as a power of 10. So you can see here where this is a very, 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 very tiny number, and when it's written out, it is very long. So here's where using exponents might actually make this a little bit easier to understand, because it's really easy, especially if you had to write this number down multiple times, it'd be very easy to miss a zero or miscount something somewhere. That's why we use these exponents to show really large or really small numbers. So let's use what we know already of place value. So if you look at how many places there are past the decimal here, you see that it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know that this is 1 over, and then 1 with 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just like 1/10, 0.1 would be 1 over 10. 0.01 is 1 over 100. Same thing. The number of places past the decimal tells you how many zeros there are after that 1. Well, that also tells you what power of 10 this would be. This is 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we just want this as a power of 10. We don't want it as a fraction with a power of 10, so we would still rewrite this as 10 to the negative 10. Okay. Numbers that do not contain exponents are written in standard form. Numbers that do not contain exponents. However, when dealing with very large or very small numbers, it is difficult to keep track of place value. Scientific notation uses exponents to represent very large or very small numbers. A number is expressed in scientific notation when it is written as the product of a factor and a power of 10. The factor must be greater than or equal to 1 and less than 10. So in symbols, scientific notation is a times 10 to the n, where a is between 1 and 10, or could be exactly 1, and n is an integer. So for example, 3,500,000 is 3.5 times 10 to the 6th, and 0.00004 is 4 times 10 to the negative 5th. And you've probably seen this before with scientific notation, but if you look at how far you need to move the decimal, that will tell you the exponent on the 10. So, and that's just like what we saw in example 4 up here. We looked at how many places to move the decimal, and we eventually ended up with 10 to the 10th because we moved the decimal 10 places. So here, we'll move the decimal 1, 2, 3, 4, 5, 6. And we move it between the 3 and the 5 because 3.5 is between 1 and 10. So we move this 6 places to get 3.5, and this would be 10 to the 6th. Now, if you have trouble remembering whether this exponent should be positive or negative, think about it this way. This original number was a really large number. We should have an exponent that shows that we're making that number bigger. So 10 to the positive 6, not negative. Here, if you look at how many places to move the decimal, we move 1, 2, 3, 4, 5. And again, right past the 4 because 4 is between 1 and 10. And this would be negative 5, 10 to the negative 5, because this number is very, very small. So if I have 4 times 10 to some power, this power needs to show that the actual number in standard form is smaller than 4. So that's, I think, the easiest way to think about scientific notation and whether you should move decimals to the right or to the left, and whether the exponent's positive or negative. Just think about the difference between a number being really large versus being really small. Okay, so let's go ahead and turn to the next page, and we'll do a couple examples of scientific notation. Express each number in standard form. Okay, so the first one, we have 4 times 10 squared. And we know that with the 4, the decimal is right at the end, just because it's a whole number. So we want to move the decimal 2 places. And this is 10 squared. This is a large number because the exponent's positive. So I want to make this number larger to make it equivalent to this. So I'm going to move the decimal 1, 2 times, and I'm going to get 400. 4 times 10 squared is the same as 400. Okay, let's do the same thing with b. We have 5.94, and we're multiplying that times 10 to the 7th. And again, because it's a positive exponent, we're going to be making this number larger. So we'll move 1, 2, 3, 4, 5, 6, 7 places. So we have 5, 9, 4, and 1, 2, 3, 4, 5 zeros. 59,400,000. Notice, by the way, a lot of people get this misunderstanding of scientific notation. This number does not tell you how many zeros go at the end of the number. It worked for this one because the 4 was the last thing before the decimal. The 10 squared, there were actually only 2 zeros. But here, if you just looked at this and said, oh, 7 zeros because it's 10 to the 7th, that would not work. There's only 5 zeros at the end of this number. So just be aware that that will not work for most numbers in scientific notation. Alright, let's do C. We have 1.3 times 10 to the negative third. So starting with 1.3. Now we have a negative exponent on the 10, which means that this number needs to be smaller. So we don't want to move the decimal to the right. That would make the number larger. We want to go 3 places to the left. So 1, 2, 3. So this is 0.0013. Okay. Example 6 says to express each number in scientific notation. And again, think about the difference between large numbers and small numbers. 900 is a large number. So we move the decimal 1, 2 times, because 9, we want to stop right after the 9, because 9 is between 1 and 10. And this is times 10 to the, we move this 2 times, and this is a large number, so positive 2. For 18,900, the decimal starts at the end, and we move 1, 2, 3, 4 times, because 1.89 would be between 1 and 10. So 1.89 times 10 to the, we move 1, 2, 3, 4 times, and this is a large number, so this should be a positive exponent, 10 to the 4th. We have 0.000064, so we move the decimal 1, 2, 3, 4, 5 places, right past the 6, because 6.4 is between 1 and 10. And we move 5 places, but this is a very small number, so this should be a negative exponent. 6.4 times 10 to the negative 5th. Alright, so there's 2 try-it-yourself problems for you to work through. Pause the video, work through those 2 problems, and then press play to check your answers. Okay, for A, this is 300,000. For B, 43,950. And for C, should have 0.000679. So it's 1, 2, 3, 4, 5 zeros, and then 679. Okay. For try it yourself number 6, in scientific notation, this one is 8 times 10 to the 5th. This one is 6.4 times 10 to the 4th. And then 1.19 times 10 to the negative 2nd. Alright. Let's do another example. Example 7 says about 1 times 10 to the 6th fruit flies weighs 1.3 times 10 squared pounds. How much does 1 fruit fly weigh? Write in scientific notation. Okay. Well, anytime you're doing operations with scientific notation, we'll be able to group things into similar parts. Whether it's multiplication or division, you'll be able to group the numbers to make the calculation easier. In this case, let's think about this. Let's ignore for a minute that these are numbers in scientific notation. we have a whole lot of fruit flies that weigh a certain number of pounds. We want to know how much does one fruit fly weigh. Well, if we had these in nice, normal, easy to understand numbers, let's say we knew 5 fruit flies weighed 10 pounds. If I asked you how much one fruit fly weighed, most of you would probably quickly tell me 2, because you divided the 10 pounds by the 2 fruit flies, or the 5 fruit flies. So we're going to do the same thing here, it's just our numbers don't look quite as nice. We want the total weight of all the fruit flies, 1.3 times 10 squared, divided by the number of fruit flies, 1 times 10 to the 6th. And here's where I said this will actually be quite easy, because notice this is all multiplication and then separated by division. Well, we can actually group these together. So we're going to divide these, and we're going to divide those. So what we get, 1.3 divided by 1, we know is 1.3. And then 10 squared divided by 10 to the 6th. Well, this uses the rules that we learned in section 9.3. We have 2 powers that are divided. They have the same base. So we know that we just subtract the exponents. 2 minus 6 is negative 4. And you always want to verify this to make sure it's actually in scientific notation. The big thing to look for is that this number is between 1 and 10, which it is. 1.3 is between 1 and 10. Okay, and this will work the same way for multiplication. It's very similar, but for multiplication, again, you'll just group things together so that you would, if I had to multiply this number times this number, I would multiply 1 times 1.3, and then I would multiply 10 to the 6th times 10 squared. So whether it's multiplication or division, it really doesn't matter. It'll still be grouped the same way. Okay, so go ahead and pause the video and work through try it yourself problem number 7. Again, if you're thrown off by the really large numbers there, just think of it in terms of much smaller numbers to make that make more sense, and then work through that problem similarly. So pause the video, work through this problem, and then when you're ready to check your answers, press play. Okay, for this one you should have gotten 1.35 times 10 to the 3rd meters. Okay, let's look at one last example. And we want to compare numbers in scientific notation. Sometimes we want to know which numbers are bigger, which ones are smaller. We first want to compare the exponents. If the exponents are positive, the number with the greatest exponent is the greatest. Because remember, if the exponents are positive in scientific notation, you're using that for large, large numbers. So the number with the biggest exponent would be the biggest number. If the exponents are negative, the number with the least exponent is the least. So the farther away the exponent gets from 0, negative 10 versus negative 15, the one with the least exponent, like negative 15, for example, would be the least. So, again, because the scientific notation with negative exponents is used for really, really small numbers, the more negative that exponent, the smaller the number. If the exponents are the same, you have to compare the factors. So, the actual part that's multiplied by 10 to whatever power. So for example 8, the table shows the weight of protons, neutrons, and electrons. Rank the particles in order from heaviest to lightest. Okay, so we're trying to order these numbers. So let's look first of all at the exponents. And we see that we do have one that's different from the others. We have a negative 31. And because we have negative exponents here, if the exponents are negative, the number with the least exponent is the least. So this is the least exponent of these 3. So this one is the least. And now of the 2 that are left, they have the same exponent. So if the exponents are the same, compare the factors. Let's look at the 2 factors. This is 1.672, and this is 1.674. So, because this number is smaller, this will be smaller than this one. So this will be the greatest. Okay. So in order from heaviest to lightest, heaviest would be the one that has the highest weight or the greatest weight. So that would be the neutron. And then the one in the middle is the proton. And the lightest would be the one with least weight, which is the electron. Now remember, this negative exponent here does not tell you the sign of the actual number. It just tells you how many places the decimal is moved when it's written in standard form. So if that looks a little confusing as to why this one wasn't even smaller than this one, because we're talking about something negative, remember that this is not telling you that the number is negative. So if you were to write these both in standard form, they would both be very, very small decimals with lots and lots of zeros at the beginning, but this one would end in a 2 and this one would end in a 4. And they would both be positive numbers because there's no negatives in front of this. So this one would be greater than that one because the 4 is bigger than the 2. So when it comes to this part, if the exponents are the same, compare the factors, you don't have to worry about one being positive or negative or anything like that. It doesn't matter what the exponents are. If the exponents are the same, whether positive or negative, just look at the factors, and that will tell you which one is bigger or smaller. Okay, so pause the video, work through the last try it yourself problem, and when you're ready to check your answers, press play to continue. Okay, these 3 planets in order from greatest to least. The one with the greatest diameter is Saturn, followed by Uranus, and then Neptune.